In today's video, we'll be looking at mole balance and design equation for reactors. So with the mole balance, we are going to look at the general mole balance equation. Just like the mass balance approach. So with the mole balance equation, we are looking at the rate of flow in minus rate of flow out plus rate of generation. And this should be equal to accumulation. With the rate of accumulation in the reactor. So anytime we have any reaction, so A going into B, and then the mole balance is for the reactants, right? So FA naught is representing the inflow or the rate of flow of A into the reactor minus the rate of flow out will be FA plus, so our G is representing the rate of generation. So generation of A in the reactor due to chemical taking place or chemical reaction taking place in the reactor. And this should be equal to the accumulation, right? So dNA over dt. So now we are using the NA here because here is the number of moles which is being left in the reactor, not flow rate. This is flow rate. So when you have a reactor, the amount of A entering, the amount of A leaving, but then there will be accumulation of A in the reactor. And this isn't flow rate, but then it's number of moles. That's why here is the NA. So the NA represents the number of moles which is being accumulated in the reactor. And then the T is per time. But FA naught here is the rate of flow into the reactor. And FA the rate of flow of A out of the reactor. And DA is the generation due to a chemical reaction. So now this becomes our general mole balance equation. So let's come to our generation. So now with the generation, when we take any reactor, right, at each point in the reactor, say point 1, point 2, point 3, point 4 in the reactor, the rate of generation differs. The rate of generation A supposed to be in mole per second, right? And this should be equal to your rate. But now your rate is in mole per meter cube second. So you need to multiply it by the volume of the reactor, right? Now, but then at each point in the reactor, the rate of generation differs. But then we want the overall rate of generation. So our GA will be equal to R dV, and then we are going to integrate the whole volume of the reactor. So now from this point to this point, we're going to sum everything up, right? And then we will get the overall rate of generation. So you can put this back into our general mole balance equation. And then we're going to get FA naught minus FA plus integral from 0 to R, sorry, 0 to V R dV, and this will be equal to accumulation dNA over dt. So this is the general mole balance we'll be using. Now, what's the essence of this mole balance equation? The mole balance equation is going to help us design our reactors. So this is the general one. So depending on the type of reactor, then we modify the mole balance equation to suit the particular reactor we are looking at. And the reactors we'll be looking at here will be, there are two main types of reactors. So we have the batch reactors or closed reactors. And then the second type of reactors, we have the continuous flow reactors. Now, because you know what a closed reaction is or a closed system is, then definitely I guess we understand what batch reactor means. With a batch reactor, it operates under a batch process or a closed system. And then with the continuous flow reactors, it operates under a continuous system. Now with the continuous flow reactors too, we have different types. We have the CSTR, and that is continuous stirred tank reactors. And then we have PFR, and that is plug flow reactors. And even with the plug flow reactors, it falls under a category of reactors we call the tubular reactor or tubular reactors. But then we'll be focused on just one type of the tubular reactors known as the plug flow reactors. And then the third type, we have the packed bed reactors. So PBR, packed bed reactors. So we want to design the equation for for all these reactors. First of all, you'll be looking at the batch reactors. To design it, you have to go back to our mole balance equation, and that is FA naught minus FE. The A here is the reactant because we are doing the mole balance based on one species, right? So if you have a reaction A going into B, you are doing the mole balance based on this species. In a different reaction, if you have A plus B going into something, you are doing a mole balance based on species A. Right? You can also do it based on species B, but you also take note of something here that anytime we have a reaction which involves two or more reactants, so let's say A plus B plus C going into C, going into D, right? And then A has 20 kilograms, B has 30, and this has 40. Now, if we are saying that A plus B plus C should give us D, and then during the reaction, all of A gets used up, right? So A gets finished to 0, and then this is left with excess of 10, and this is left with excess of 20. Would B and C give us D? No. So anytime one of the reactant gets finished or gets used up, then the reaction ceases, right? So it means that our mole balance will always be based on the limiting reactant here. So just one species, and that's what we are doing. So we go back to our mole balance. Fa naught minus Fa plus integral from 0 to V R dV should be equal to dNA over dt. Now, because batch reactors operate under batch processes, we know that with the batch process, there's nothing like flow in and then flow out, right? So when you have a batch reactor like this, we just feed in our reactant and then we close it. And after a certain time, we just come and look at what has happened to our reactant and look at the number of products which has been formed. So there's nothing like flow in and then flow out. So our Fa naught and our Fa will be equal to 0 because there's nothing like flow in and flow out. However, these terms still remain. So integral from 0 to V R dV should be equal to dNA over dt. And we know that for batch reactors, there is always accumulation. When we integrate this, we are going to get RV from 0 to V, and that should be equal to dNA over dt. And then we are going to have upper limit minus lower limit. So RV minus R times 0, that will be 0. So this should be equal to dNA over dt. So we can make dt the subject, and then we'll be getting dt is equal to dNA over RV. And when you integrate from 0 to a certain time t, now this time t refers to after what period or after what time should we come and check our reactor. So that will give us t minus 0, right, to be equal to dNA over RV. And then since we are integrating from 0 to t, so it means that at the start of the reaction, T equals 0, right? So when T is equal to 0, our NA here will be NA naught, right? And then when T is equal to time T, which is the upper limit here, then our NA here will be equal to NA, right? So let me just call it NA1. So here too, we are going to integrate from NA naught to NA1, right? But then once you are looking at accumulation, for batch reactors, we feed in our reactants. So let's say at time t equals 0, we have a lot of accumulation, right? And that is the NA naught. So it means that NA naught will always be greater than NA1. And after a certain time t, your NA1, right, will have to reduce. So this means that, and we know how integration works. So we can't integrate from a lower value to a higher value, right? So we can reverse it and say our t is equal to integral from NA1 rather to NA naught. And then when we reverse it, then we have to negate it, minus the NA over RD. So we can bring the negative sign to the denominator, and then we'll be having integral from NA1 NA naught dNA over negative RV. And then in our previous video, we said that negative R here becomes the rate equation based on the reactant. Now this R here is our rate equation. So for batch reactors, the design equation is T is equal to integral from NA1 to NA naught dNA over negative RV. So this becomes our design equation for batch reactors. So anytime you have any problem concerning batch reactors, we are most interested in the time to take for the reaction to cease. So for that, we are going to use this equation to model, and then this is our rate equation. So we can find for a rate equation, which is negative R is equal to K C A exponent n, where your n here is the order of the reaction with respect to A, and then our V here is our volume, and then our the NA here is our mole. So we can integrate, and then we get it. Now our next reactor is the continuous flow reactors, and then we'll be looking at the CSTR. Now we have to go back to our more balanced equation. So FA naught minus FA plus integral 0 to P RdP should be equal to dNA over dt. Now since CSTR operates under continuous process, we know that definitely there is going to be flow in and then flow out, but there won't be any accumulation here because CSTR mostly operates under steady state, and when there's steady state, there is no accumulation, right? So this part goes to 0, but then this part and this part remains. So we are left with FA naught minus FA plus integral from 0 to V R dV should be equal to 0. When we integrate this part, we are going to get FA naught minus FA plus RV should be equal to 0. So we can transpose this to the right hand side, and then we'll be getting negative RV should be equal to FA naught minus FA. And then we can divide through by the rate. So our V is equal to FA naught minus FA all over negative R. And our negative R here is the rate equation based on the reactant. So in this case, it will be based on A, right? Because A is our reactant. So all over minus RE. So this becomes the design equation for continuous stirred tank reactors. Please take note of the design equations. So our next one will be PFR, which is the packed, that is the plug flow reactors, PFR, plug flow reactors. So the plug flow reactors, with the same approach, we have to go back to our more balanced equation. So FA naught minus FA plus 0 to V R dV should be equal to, now because you are using E, so let me just write RA dV, and this should be equal to the rate of accumulation. Now when you take, previously I said that the plug flow reactor is a type of a reactor known as the tubular-like reactors. So the tubular reactors, so we have, so they are tubes, right? And because this is not a continuous state tank reactor, with a continuous state tank reactor, because we have a stirrer present in it, so the rate in the reaction doesn't differ, right? Because the reactant mix very well. But now with the plug flow reactors, the rate in the reactor differs, right? So now we are going to choose a very small volume that will make the rate not change. So if I consider just this volume, then I can see that at each point in this volume, the rate wouldn't change. And then if I consider this point and this point, the rate will change because there is no stirrer here. And then with the continuous state tank reactors, because there is a stirrer, right? So there's always a stirrer in the continuous state tank reactor. Then that stirs the component present in the reactor. So always there is a uniform rate in the reactors. But then with the plug flow reactors, we can't see same for that, right? So I want to choose a certain volume here and see that at this point we are calling it V. Then at this point we are calling it V plus change in V. So that from this point to this point becomes our change in V. Right? So even though we are feeding in our initial flow rate of A, at this point we are going to get our A entering and then our A leaving. Right? So we are considering just a small portion. At this portion, you are going to see that because you are considering this portion, you are going to get something like, even though we are going to use our more balanced equation, our FA not entering, this is for when we are having our reactor and then it's actually entering. So when we are considering this and then this, then we are going to use this. But then since you are looking at just this volume, you are going to see our FA not is entering here. But then here will be FA entering at this volume, right? Minus, because you are considering this volume. And then at this part it's leaving, but it will still be at FA. But it's leaving at this volume, V plus change in V. Right? So this is what you are looking at for this portion, plus our integral from 0 to V R A dV is equal to dNA dt. Now, when it comes to the generation part, this term from 0 to V R A dV, that part also you have to modify it because you are not looking at the whole volume of the reactor, you are just looking at this portion. Right? We are going to integrate from, so in actual sense, you are supposed to integrate from V, this point, to V plus change in V. So this is what you are supposed to do. Now, when you have any integral from A to B, it's the same as you substituting from 0 B minus A. Right? So this always works because at the end it will be the upper limit minus the lower limit. So we want to put everything together. So when you put everything together, we are going to get this being equal to from 0 to change in V. Because when you subtract this from this, the V and the V cancels out and you are left with this. So from 0 to V R dV, right? So dV. So this is what we have, and we are going to put in that here. So we are going to get the mole balance for plug flow reactors will now be FA entering at this volume minus FA leaving at V plus change in V. And this plus our generation term now becomes this: integral from 0 to v, change in v, r dv, and this is equal to the rate of accumulation. Now, black flow reactors is also a type of continuous reactor. Now, this part goes to 0. There is no accumulation. So we are left with FA entering at V minus FA plus change in V plus. And when we integrate this, we're going to get R change in V because this part is 0 and this should be equal to 0. When we arrange it well, we are going to get F A. So let me arrange it so we can get something like, you can transpose the whole of this to the right hand side and we'll be getting R change in V to be equal to FA V plus change in V minus FA V all over change in V. And then we can get our R to be equal to FA V plus change in V minus FA V all over change in V. Now when you look at this, then it mimics a differential term. So when we want to, for differentiation, we know that there's always f of x plus a certain change in variable, right, minus f of x all over change in x, right. So this is what we are seeing, and this is actually equal to df over dx, right, and this mimics this. So you can say our r here will be equal to dfa, right. So now this is our f, so this is our fe here. Our x here represents our v, and our change in x here represents our change in v. All over change in v, change in x. So this mimics this. So it becomes df over dx, so all over dv. And this becomes the design equation for plug flow reactors. Yeah, so we will end it here. The next time we continue.